Hello, everyone. This is Wei from the SciLifeLab and the KTH University in Stockholm. It's a great pleasure to do this online workshop with you during the I2K conference. So today we're going to focus on a new tool called BioEngine for web and AI-powered bioimage analysis. I'm going to quickly introduce you what is BioEngine, and then we move on the hands-on tutorial on how to use the BioEngine. As you know, there are many challenges in AI tools for bioimage analysis: usability, flexibility, interactivity, scalability, and also in most of the cases, we also care about the data privacy. There's also a lot of a trend going on in the bioimaging field. For example, most of the tools start to adopt deep learning methods, and many of them even start to go with these very large models, such as transformers for computer vision tasks. And because we are training AI models, we are dealing with massive data set, and microscopes are producing a lot more data these days. And there's also a trend that moving towards more scalable image file format, such as SAR, M5, NGFF, for example. And all in all, this brings us into a future of web and AI-powered bioimage analysis, because in order to handle all these large models and massive data set, it's inevitable that we're gonna run into the computation in the cloud, such that we can scale better in the future. There are many existing solutions. You might already using many of them. For example, there's desktop software, ImageJ, Elastic, Napari, for example. So they all try to run with the deep learning libraries, but there's still issues. For example, it's still very hard for the users to install, for example, GPU drivers, CUDA, and all those are kind of very hard for non-expert users. And there's also notebook solutions, including the ones runs in the cloud. For example, the free Colab from Google even provide free GPU. And then there's a zero cost, which built on top of Colab. There's also Jupyter Notebook Binder, for example, is running in the cloud. With Jupyter Notebook, you can also run it locally, which will require similar requirement if you want to set up a GPU as the desktop software. There's also web replication. For example, there are a couple of methods already providing this kind of demo websites, like such as Nucleizer, cellpose, DeepCell. And there's also ImJoy, which is I have been leading the development. So ImJoy is a similar effort. We try to bring together the Python ecosystem and the web. So it's a web-based framework which you can run, install different plugins, and then in the it can run directly in the browser without any installation. So it's easy to share with the URL with your tools, and it can also connect to the cloud. Right now, we have more kind of putting more efforts to build a more solid framework for running computations in the cloud, including this one, the BioEngine we're gonna talk about later. There's another effort, which is a community-driven project, which I have been working on together with several others within the bioimaging community. This is the BioImage Model Zoo project. It's basically a repository for sharing AI models for bioimage analysis. And this is the website. So I will just briefly mention it because but feel free to visit this website, and you can find a lot of bioimage analysis models where you can download and use in different software. So today we're gonna focus more on the BioEngine. So BioEngine, which originally has been developed for many for running models for the BioImage model zoo. And now it becomes more generic solution for performing scalable AI model serving. And this is a framework of it. So the key thing is that it's a set of Docker containers running within a Kubernetes cluster, or locally you can use also Docker Compose. And it has three key components. One is the Triton inference server, which perform the actual model serving. So it's a Docker container provided by NVIDIA, and we did some custom development on top of it. So it supports a lot of different popular frameworks such as PyTorch, TensorFlow, many models, Onyx, for example, and it manages the GPU and model execution. So the way we incorporate this server is that we build around an ecosystem, including connect to the BioImage model zoo, such that all the community contributed model can be directly used from within the Triton inference server. And through the API, we built another web service called Hypha, and this is basically a communication hub or user management and also workspace management to handle and orchestrate different services within the Kubernetes cluster. And I have another talk about Hypha, and I can post the link later so you can get more details about Hypha. But for now, Hypha is just a communication layer on top of the Triton inference server. So it provides this proxy allows the user to access from a lot of different clients, including the desktop clients, different software, Elastic, Napari, DeepImage, QPass, and there are more and more we are supporting and we have been working on. And for the web client, it's more interesting because it doesn't require installation. And this is made possible because of two reasons. One is that the development of the new web standards, such as WebAssembly, which allows run, for example, Python directly in the browser, and it enables a Jupyter notebook environment, runs completely in the browser. And then we have also different plugins in ImJoy, which can help this kind of GUI development for the, because the heavy computation is all on the server side. So it makes it possible to run with even lighter client side application. But we support both type of them, desktop clients and web clients. So all these different clients talk through Hypha, and Hypha gonna do load balancing. For example, if you have a multiple Triton inference server, and then it will just balance the load across different servers. And all these servers gonna connect you to the model repository hosted on Zenodo for the BioImage model zoo. The way we kind of envisioning is where BioEngine can be deployed both in the public cloud. For example, it can be commercial cloud, AWS or Azure from Microsoft or Google, for example. And then this can allow public access or with authentication. And the other way to deploy the BioEngine is that I think it's more interesting for many of the users because they can deploy their own instance in their institutions, mostly with Kubernetes. But we also provide another option, allows you to even smaller scale deployment where you can just run the BioEngine on a workstation owned by the group, for example. But the key idea is that to make it more, provide a more flexible way of deploying this BioEngine, and then it can be used by many different applications. The key features which worth highlighting from the BioEngine is a framework support many models. So we can even mount the entire repository from the BioImage model zoo which now has at least 20 or 30 models, but the list is keep increasing rapidly. It's a multi-user framework, which is different from other solutions like Jupyter Notebook or other desktop software, which is designed for a single user with in mind. And this is a many user solution, can be run simultaneously, and many applications. So you are not like conventional web application where you can more typically just design a specific application. And this is, we are aiming for a generic framework for many different type of application, different data types, and share GPU resources. The server gonna share the GPUs and across many users, across many models. And this is important if we want to provide a service, or if the, for example, institution want to provide a service to improve the utilization of computational resources. And this is very important for the scaling of the services. And we support both inference and training. And actually Triton inferences server, which we use, the key part, and it's original design for inference server, inference only, but we had did some additional work to make it also work for training. This is very also interesting feature because this allows more like collaborative training. For example, multiple users, they can annotate and then send the data to the same server and to train the same model, for example. So we also support local and cloud deployment. So you can have on your own workstation, institution, or use the cloud provider running in the cloud, for example. So yeah, so in the next section, we're gonna show you basically a tutorial, and feel free to follow when you get this tutorial. When you see this video, I guess you will get the link, and feel free to open the link with the video on the side, and then you can just, you know, follow the tutorial with me. So in the next slide, we have this getting started tutorial. If you click this button directly in the browser and just wait for a bit, and you will get this Jupyter Notebook interface. And this is actually a Jupyter Lite, which is different from Jupyter Notebook. One big difference is it doesn't need a server. So it's a set of static files powered by this technology called WebAssembly. And there's a Mozilla project called PyODI that allows compiling, for example, Python libraries such as NumPy, SciPy, and all those scientific stack to run in the browser. And this is the JupyterLab version called Jupyter Lite, which we also did some customization, for example, adding ImJoy support to the notebooks. But anyway, this is the environment we're gonna focus on during this tutorial. So on the side, you have the files. When you open this notebook, it will just automatically load this file, which is this one. You can modify, but if you want to reset the notebook, and you can click this button called reset. And if you reset, just be aware that if you did some modification, and even if you save it, it will be cleaned up for this. So just be careful about that, unless you really want to remove everything and start from scratch. Then if you want, just avoid clicking this, and so you can keep your data in the browser. So yeah, so let's get started, and we can close this sidebar. And then this is just a normal notebook, right? If you press Shift and Enter on this cell, or press this play button, and you can run it. So, so the BioEngine is a server, right? So here we are not working on the server, but we try to use the server, and we're gonna provide in kind of demonstration server. So in this notebook, we're gonna demonstrate how we can interact with the server and use it for perform common bioimage analysis task, for example, segmentation. So we first run this cell, and this will essentially install this library. It's a client library used to talk with this BioEngine. It's called PyTriton client, and Triton is the server which we just mentioned, right? And there's some utility tools. So, and this code can also run if you download this notebook, and right, if you download this, and you can also run it with your native Jupyter notebook later if you want. But this is just, it's not necessary for this tutorial. So for this tutorial, just run it, Shift and Enter, and you will see this dot here. If it becomes black, like now, it's idle. And then if it becomes black, it means running. So it means you need to wait for a bit. And sometimes you also need to restart if it doesn't, sometimes it can kind of stuck, for example, and then you just need to restart, which is not the same as Jupyter notebooks, right? So it's, yeah, so then we import the library, and then we just run cellpose. So cellpose is a popular cell segmentation model, which is which they call the generalist model, means you can run without retraining, you can run, use it to segment a large variety of images. So here in this case, we just download an image, which is here, right? So this is the link of it. And you can open it later if you want to see. So it's downloaded, and this is the shape of it, right? The size is a 3-channel image. So now, in order to use the BioEngine, we just need to call this function called execute, right? So this function is imported from this Triton client, right? So, and then in the argument, the first argument is a list of input. So the first input is an image. We transpose a bit to make sure 3 is in the first dimension, and then the other 2 is in the second, third. So this is why we have this transpose here. This is a requirement for run this cellpose model. And importantly, we need to specify the name here, right? So it's cellpose Python, because it's and this is the URL of the server. So because the server support many different models, the same server so that's why you need to specify this model name. And there's the other parameters which we're gonna pass it into. If you know a bit about cellpose, you know that there's an important parameter called diameter. Sometimes you will need to tune a bit on the size to match the nuclei size in your image, for example. If we just run it, right? So then so you see it quickly returns in 1 or 2 seconds, right? So it's get the prediction, and this is the mask. So now if we just run this, and we're gonna get this result. So you can see on the left is the input image, on the right is the predicted mask. So because it's a multi-model server, and we can also change the name to stardist, sometimes you will need to change the image shape as well, and as well as types, because each model has different inputs in terms of size, shape, channel number, etc. But they are similar. You just run this execute function. And then if we run this, right? So in this case, we just make the prediction, we get the mask, and then we display side by side. And this is the stardist model, which is also quite popular within the community to run nuclei segmentation, for example. And this is just an example. So the image is essentially NumPy array. So you can also load it locally. If you have some images locally, you just use some other Python library like ImageIO or Pillow to read your local TIFF files, for example, and you just need to make a NumPy array and then pass it to this execute function with similar parameters here. So, and then in the next, we have shown you two of the segmentation models, and now let's try a classification model. So this is a the human protein atlas single cell classification model, which we obtained from our challenge. So we all hosted a challenge last year for on Kaggle. And this is actually a Wei model, which does protein localization classification, and we will see how it looks. So we just define some kind of labels such that we can translate the prediction into the actual labels. So these are the protein pattern labels. They are different organelles or compartment in the cell. And then we have different, we define a function to get the image from the human protein atlas. We just run it, and then we're gonna run this to get an image from the human protein atlas. And then because this model is doing single cell segment classification, so that's why we just for demonstration purpose, we crop it in to contain only one cell, right? So we just run it and we get the image. And then we can just run this to run classification. So the difference is that we changed the model name here. Now is this Inception V3. This is a model architecture. Best fitting is the team who made this model, the winning team of our challenge. And this is the entire model name. So then you pass the image. Yeah, and then you get the result. And in this case, the result is not an image, but a kind of probability. So in here, we just decode the prediction, apply a threshold, and then we get this cytosol. So this means that the green channel localized in the cytosol of the cell, for example. Yeah. So this is the first example, and I showed you 3 different models, but they are all being accessed the same way, right? More or less similar. So you run this execute with different, requirement on image, input image, for example, but they are quite similar. So the key thing is that you install this library and then you import the execute and then you run the execute. This is the only thing you need to keep in mind in order to access the BioEngine. So what happens is that when you access this, the image is gonna send to our demonstration server. So later, if you have your own instances, will just run on your own instance. We're gonna coming back to that once we released the BioEngine. So the next tutorial is about training. So here, I'm gonna do it quickly because just for demonstration purpose. And this is a quick demo that's showing you not only for prediction inference, but we can also perform some sort of training on the BioEngine side. I will just quickly run through this demo so you get a feeling about it. So we prepare a set of different functions. Importantly, we have this train, predict. I will not go through line by line for now. And we can also download the trained model, right? So, and then for demonstration, we download a data set with a few images, and you can visualize how it looks like, right? So the training sample, it consists of several kind of images, four images for training and 4 images for testing. And this is the input image, and this is the label. So actually, this is not predictive mask, but the actual human annotated label. So this is the training data. So we feed in the data, 4 of them, right, in pairs, and then we train the cellpose model. So if we just run this now, so what this code does is I call this train function. It has a model ID, and you can specify a new one. It will create a new model if you change into a new one. But this is a kind of identifier for your model. And then we pass in the training sample, which is 4 images with input and the labels, right? And here we said we want to run 10 epochs, right? And then we don't use any pre-trained model for now because just for demonstration purpose. In practice, I mean, you will likely use the pre-trained model, for example, Cyto, right? title, which is the cellpose model, because we are using cellpose. So this is the official cellpose model. If you use Cyto, for example, and I will put it back to as norm. So once we train, and then we're gonna use the same model ID, we can do prediction with this test samples, right? So test samples, we only feed you one image to do the test, see how it looks, right? So while it's running, we have 10 epochs. So I will just go back to show you how it actually looks in the code in the meantime. So it's very similar to our previous tutorial. We just install this Triton client, right? And then with the Triton client, we have this execute function. But in this case, we also use this sequence executor, because execute means that you run only once, and then you have this, because training is more like a sequence, right? So that's why we have another function. It's a class, and then you can see how it works. So in the train function, for example, we instantiate this sequence executor, and then we specify the name, and this is the signature is essentially the same as this execute function, and you get this sequence executor. And then during each epoch, and we take one sample, right? And then we generate an input. So these are the inputs. But in addition to the image and labels, we have these parameters, and we specify how many steps we want to have, right? So it means one sample gonna run 16 steps. And in this case, we're gonna do augmentation. So the same image pairs gonna augment 16 times and train the model, right? And these are different other parameters, which is the same as before. And then we run one step, and this is the step. And then we get the result, and the result is not the image, it's actually the loss function, loss value, right? So that's why we append these loss values along with other information, but here we only keep these loss values. And then we compute an average loss for the entire training set, which has only 4 images in this example. So you can see that, yeah, so this is how we do the sequence executor. And why we need this sequence executor, because it will block the server for a while, so others will not have access to this, specific model, right? If we only have one instance for the Triton inference server, that's gonna be the case. And then we have this predict function, which is similar. We just, predict with this step, right? So you just feed in the input data and then trying to get the result. And in this case, the output is actually the mask. So yeah, so let's see, we went for 10 epochs, and then you can see the loss value is actually decreasing, right? From 0.4543 to 0.36, right? And then this is the prediction. Yeah. So when you run this predict, you get this result, which is good. And then optionally, you can download this trained model, and I will just run it for now. So the way it works is that we're gonna export this model, and this is the exported model actually is compatible with the BioImage model zoo specification. So we have this so-called resource description file format, and allows us to enable cross-compatibility between different consumers. So you can download the model, and then here with ImJoy, we can even display a file browser. So the model is downloaded in the browser. So in order to actually download it to your hard drive, right, local hard drive, and in your file system, you need to do this download, right? And then you will get this actual model. If you unzip it, you will see several files. I will skip doing that now. So then, yeah, we have the model now. You can use it in other software, for example, if it's compatible. And then you can also perform this testing on it to see how it looks for other samples, because we have 4 samples, right? So yeah, so this is how it looks. Yeah, so yeah, so this is just a quick overview on how to, do training with this. In this case, is cellpose. We don't support all kind of other models for now, but as a demonstration, if this works well, and then we will keep improving and more and add more and more models which does support training. All right, so let's move on to another tutorial, which is yeah, so this is just to demonstrate how you can, because we all show code, but many of the users when we build the tools, we do want to make it more accessible for non-expert users, which doesn't know any of the programming language, or you don't even want to show the code, right? So in this demo, we're gonna show you how we could use ImJoy and Kaibu, which is Kaibu is an ImJoy plugin to build a GUI which runs in the browser. This the same pattern, right? We just install this Python client, and Kaibu is just some utility tools we're gonna use later. And then we fetch an image. This is an example image. We just displayed from the human protein atlas. And then we test this cell segmentation function, right? It will send the image to our BioEngine, and it will obtain this mask, right? So, and then we display the result. It's important we need to set 100 because you see the cell size is roughly 100. That's why we need to set this importantly. So in the next cell, we have this ImJoy plugin, and if you run it, you'll see how it looks. So this actually opens this Kaibu. If you run it locally, make sure you see this icon, the ImJoy icon. Otherwise, you will not see this Kaibu. So what we did here is that we create this viewer with Kaibu, right? So this is the way you create the viewer with Kaibu. And then with this viewer object, you interact with it. Let's say I want to visualize this NumPy array image, which is we see here, right? So in order to create some kind of interactivity for the user to click, and here in this example, we add a control element, which is the button. The type is button, and the label is do segmentation. This is why you see it here, right? So then when we click this, and we will call this function specified with this callback field. So this is the function, do segmentation. So this is the do segmentation function we define. And then we just run it. Run the cellpose segmentation. We pass the image, we get the mask. And with this Kaibu utility function called mask to features, we're gonna convert this mask image to a set of polygon coordinates such that we can add a shape layer in the Kaibu plugin such that we can display it. For example, if I click it now, right? So what's gonna happen is that run cellpose segmentation, convert the mask into a polygon layer, and then we add to the Kaibu viewer, right? So that's, if we scroll up, and then we'll see this red thing here, right? So you can see that it's actually a bit pixelated because we downscale the image, but just to make it faster, right? So, and you can see that these are different layers, right? The I2K-2022, this is actually the image layer. And then we have the annotation, which is empty for now. The idea is we're gonna support annotation, manual annotation in a interactive annotation setting, for example. But anyway, we can remove this to avoid confusion. So basically we have 2 layers, the image layer and the prediction. The prediction, if you hide it, this is the red layer, right? So yeah, so you can see that And the cool thing is that you can even edit these different polygons if you want. This is useful in a interactive segmentation setting, for example. All right, so yeah, so that I hope you get feeling that how you can potentially, create this kind of GUI tool with the BioEngine. As you can see, the code is rather simple because you don't need to handle all those deep learning libraries, for example. Okay, so I mean, you can also do wrap this as a ImJoy plugin and then post it on GitHub, and then you generate a link to share with others. I will provide more information later in the comment section of this video, for example. But let's move on to the other one. So this is the last training tutorial. I will give you a quick overview on how we can combine the BioEngine and potentially do interactive annotation and training. So this is not very complete tutorial. I hope I can add more stuff into it, but for now, I will just give you an idea on how this could potentially be implemented. So the idea of interactive annotation training is that we train a model on the server side with the BioEngine. And while we are training, we do annotation simultaneously, right? So when you annotate more, you send it back. And once the model has been trained for a while, right, we can already use it to produce the initial annotation. And then we just need to fine tune it instead of annotating from scratch. But let me show you how roughly it looks. So this is just to define into functions, utility functions we're gonna use later, and we fetch an image, same human protein atlas cell image like this one. And then we create a mask image with the standard cellpose model. Yeah, so we just run the same cellpose segmentation model as before. And then we just test, and this will show you how it works with this train once function, right? We pass an image and the mask, it's gonna train the model. So we use the same model ID as before, right? So it means that we don't train from scratch, but we actually add in this image to train more with the same model, because 106 is the one we used before in the previous tutorial. So we can, after we train, and then we have this predict function, same model ID, and then we're gonna also tell it to reload because we already trained it. So this is important to see the latest model. And we show the result here, right? So, and then, but the idea is to combine these two functions together, right? Such that it will allows you to predict, and then you fine tune and then train. So this is just a quick combination of it, how we can combine it with Kaibu, right? For example, you load an image. Let's assume it's an image which is new, right? Which unseen by the network, but just for demonstration purpose, I will just use the same one, okay? So we call make prediction. This image is gonna send to the server, get this mask, right? And then we have this. So now the idea is that, for example, now because, the cell, there's 2 cells missing, right? So the idea is that we're gonna fine tune it, right? So we're gonna add this new cell, right? This should be 1. This should be 1, right? So I might be not wrong, but just for demonstration purpose, I will just add this 2, right? And sometimes you can also, I'll show you quickly what you can do, right? You can, if there's 2 cells in here, you can cut it, right? Cut into 2, now it becomes 2, right? And there are other tools you can fine tune the result from the prediction. And now let's assume we are done with the fine tuning of the images. We just click this button called do training. So this fine tune mask is gonna send back to train the model, yeah? So if I click twice, right? And it's gonna do another round, right? But anyway, so we just, I just show you this. If I do prediction now, oh, you see, we are making progress because we add this, let me remove this green thing. So this is the latest one, right? So it's actually started to detect this new one, right? So this means that the one we added is actually start to work, right? So of course we will need to do more, but as I said, this is not very complete demonstration, but just in the actual case, we will do a more training, right? So we're gonna let them model train more. But the nice thing is that while the training is on the server side, we can, in the meantime, we can do more annotation, right? So this is the idea. Yeah, so feel free to play with it. There's also a, I'm gonna post the link for the interactive, for a more complete example of the interactive segmentation. And if you're interested, you can also implement that, right? Based on change, you can change the code here and then actually play with and then work towards that more complete example. And so for the sake of time, we'll just move on. Yeah, so those are the tutorials. I think I hope you get at least get an idea on how it works, and feel free to play with these notebooks while listening to this you know, tutorial. And feel free to make changes. You can reset if you kind of messed up with the code, right? If you just be careful that you will need to, you know, it will remove everything you changed. So a quick comparison, as you already know what is BioEngine and how it works. I think one common question we get is that how does it compare with normal Jupyter notebooks or Colab, for example, right? So I think that for me, the key difference is more about scalability. Because one big issue with Jupyter notebooks is that each user gonna run on a Jupyter notebook kernel. If it's GPU based, then it's gonna, you're gonna occupy that GPU, right? No others can access simultaneously. So this is gonna be a huge issue when you want to scale to many users or provide a public service, such as the one we have in the bioimage model zoo website, right? We can't afford so many GPUs with so many users, even just 10, right? It requires 10 GPU, or you need to queue the users, and you know, but each time the user can occupy the GPU for, let's say, a few hours, even to, if we are talking about training, right? So BioEngine solves this kind of problem by not letting the user occupy it, or not letting the model occupy the GPU all the time, but it's gonna schedule it. We are still fundamentally limited by how many GPU we have, but the assumption is that in most cases, not all the users gonna use it all the time, right? Or the code will have some kind of, sometimes it perform pre-processing on CPU, right? At that time, with the BioEngine, the GPU time can be used by other models, right? So this is our kind of assumption, which works in most of cases in practice. And if not the case, we can still queue the users, right? So this is a big difference on the scalability side. It's a multi-user, multi-model service versus a single user and not single model exactly, but a single model gonna likely occupy the GPU during the course of, you know, execution of the notebook, for example. So there, here you have another list, which I listed. For example, for Colab, it doesn't support, you know, I mean, you can still do it, but it's not made for, right? So, but with the BioEngine, we can do cloud or on-premise deployment easily. It's a Docker container or Kubernetes Helm chat, which you can easily deploy. I mean, not easily by non-expert, but easily by the IT experts. It's a multi-user and which is suitable for providing a public service or shared among a group of people. And you can serve multiple models, which is very practical when you have a whole list of models such that we have from the BioImage model zoo. It's improved the GPU utilization. As I said, it can share GPU among users and models. And it's actually instant usage, right? So it's not like Colab, for example, if you use it, you will need to wait for a long time until TensorFlow, PyTorch, and everything installed, right? So you will need to wait for a long time, but the BioEngine is almost instant, right? You use it, it's always there, right? So you just use it instantly, access from one of the application client or desktop client, or through the Jupyter notebook, including the Jupyter Lite, which we have been using in the tutorial session. So in addition to the Jupyter notebooks, Jupyter Lite and the ImJoy access from BioEngine, as I mentioned, we can also access it from different desktop clients. So we have been actively working with other community members in the bioimaging field, so including the IC from Institute Pasteur. The IC team has been, especially Carlos, has been actively working with me on integrating the BioEngine access from within IC. So this is a demo which you can use cellpose. Send this image to the server, and then you click run, and then you get the result back, right? So in just a second, you get this kind of mask. This is just another example, which uses the more recent model we made, which allows us to load any of the models from the BioImage model zoo. And in this case, it's the HPA segmentation model, which take this image and then get this mask out. Yeah. So a shout out to Carlos, who has made this possible. So I just want to briefly mention that I have been working on this AI-assisted bioimage analysis, which is a cool interface, let's say, powered by natural language processing using the latest massive models called GPT-3 and Codex model from OpenAI. It essentially allows you to use voice or English to instruct the notebook, and then it can generate Python code from English. And it allows us to perform some analysis. And feel free to watch this video. I will not play it here, but yeah, feel free to reach out if you have a question, ideas. So in conclusion, I have showed you BioEngine, which is a tool for scalable AI model serving. And I have been showing you this step-by-step tutorial on how to use BioEngine. Hopefully you get a sense of it, how it works roughly. And then feel free to use it also in your own application or process your own image. Just as a disclaimer, because this BioEngine server is still in experimental state, so it might, sometimes down for upgrade or maintenance, for example. So yeah, just be aware that if you don't get it run at the moment, try it again later. So we will try to make it available as much as we can. So yeah, so that's it. So all this work has been carried out at the cell profiling group headed by Emma Lundberg at SciLifeLab in Sweden. So ImJoy has been used in this project, is a community-driven project by a few key members, Florian Müller from Institute Pasteur, Martin, who is my former colleague, Craig from the EBI, and there are many others. The BioImage Model Zoo is also a community-driven project with many different teams. So we have weekly meetings with ImageJ teams, and there's also BioImage Archive team, Fiji, ImageJ, Elastic, ImJoy, zero cost, and all these different community members has been work actively together toward this coordinated effort. So yeah, thanks to all of them for making this possible. And thank you for your attention. So we're gonna do, I guess we're gonna have a chance to have these questions later. Yeah, feel free to play with it, and then we can talk during the live Q&A session. Thank you.